Europeans' engagements happen.
Where's where are my notes? Where are my notes? I can't see my notes. Okay, Google Slides. Okay, I don't want to know. Let take part again.
Okay, so
I hope I'm not the one they are seeing. I don't want them to see me. I want them to see my notes.
You can't respond. They don't see you. Since
I'll send that to you.
we see what they are viewing themselves.
Okay, so good morning. I am. Muted myself. Okay, but I want to check just to be sure. That's a blank page.
Let's see this. Rest of the office.
No, I've discussed this yesterday.
What I mean is the other tabs. Nothing back.
Okay. So I wouldn't know. It's your
area of
expertise.
Okay, I like it. But this one is not.
Maybe you meet me first. You have to cancel the first.
Your last name. You have to go to today.
I have the coffee today. No, sorry. If I use slideshow, it won't show this. If I use slideshow, all right. Oh, okay, beautiful. All right. Good morning, my very good students. I hope you had a wonderful night's rest. So today we will continue with our study on hydrolysis of ions, which we started some days ago. All right, so in our class yesterday, oh sorry, the day before yesterday, that was on Wednesday, we tried to see okay, so sorry for the little break in transmission. All right, so we are looking at what is the effect of adding small amount of acid or a base to a buffer solution. And you could see from the illustration I gave on Wednesday that the addition of a small amount of sodium hypochlorite to the solution of the buffer changes the pH of the buffer just by 0.03. So you can see that a buffer solution is the one that resists change in its pH when a small amount of an acid or its base is added onto it. Now we've used acid buffer to illustrate this. Can we take a look at base buffer and see how that will respond, how it will respond to addition of small amount of acid or a base. And so you have this question here. Say, can you try the following? Calculate the pH of a buffer consisting of 0.5 molar hydrogen fluoride and 0.45 potassium fluoride before and after addition of 0.40 grams of sodium hydroxide to 1.0 liter of the buffer, Ka being given above. That's an acid buffer. I don't want us to bother our head with that because it's going to follow the same pattern as one we did previously. However, I want to look at this second one that says calculate the pH of a buffer. Calculate the pH of a buffer consisting of 0.25 molar dimethyl ammonium chloride and 0.30 molar dimethylamine before and after addition of 50.0 ml of 0.75 molar HCl to 1 liter of the buffer solution. I may quickly want to run you through this. Let me see how far I can go. Okay. Well, it's meant to be because there's no blank slide here now for me to solve it for you. And so it's actually meant to be an assignment for you, really, so that we don't waste our time on that. So let's make progress. All right. Sorry. All right. While I'm mounting this, the other lecture notes, please let's take down the attendance code for today. The first code for today is A342B. A342B. That's the first code for today. All right. While you wait a little bit, let me mount the second, the next lecture note. Okay, so we are gradually coming to the end of the class as far as this course is concerned, and this aspect of the course is concerned, while we look at some applications of equilibria in solution. We've looked at buffer system in our last lecture. We're going to be looking at solubility of sparingly soluble salts. Sorry, sir. No, absolutely. Okay, so we have discussed the addition of small amount of acid or a base to a buffer system. Now, how does it really work? How does it really work? I did mention, for example, when you had sodium hydroxide to an acetic acid acetate buffer. Okay, for example, you have acetic acid and you have acetate ion mixed together. That will give you what we call a buffer solution. Or for example, in this illustration I display here, you have propanoic acid and sodium propanoate. The mixture of the two of them will give you what we call an acid buffer. The question is, how does this buffer system works? How does it work? Now, for example, let's assume we are adding sodium hydroxide now, a little amount of sodium hydroxide to this system. What will happen here is that the propanoic acid will dissociate as given here. Okay, you can see the equation. Now, like I told you, this modulo stuff here is just an equilibrium constant, okay, with the equilibrium, the dissociation constant written directly on top of it. Okay. Now, my pen is not. I think I'm having an issue with the pen. Sorry. Okay, turn the pen. I've seen it. I've seen what the issue is. All right. Now you can see. So supposing we now add sodium hydroxide to this solution. Now, this is sodium propanoate. It will also dissociate to give you this. All right. So supposing we now add sodium hydroxide to this system, sodium hydroxide will react with the propanoate ion. Okay, so we're going to have, for example, sodium hydroxide, some amount of sodium hydroxide added here, or let's say hydrochloric acid added here. So let's say, let me call this RCOO minus, where R will stand for all this. Where R will stand for all this. All right, plus hydrochloric acid. Just for example, so what happened here is that you have the formation of RCOOA plus Cl minus. Now, you can see you have introduced more of the acid because of the addition of this. Okay, so the fact that you have this from the acid and you have it also from the salt, all right, the amount of propanoate formed from the salt, because the salt is it's an ionic salt, it's a very soluble salt because it's salt of sodium, it's a sodium salt, so it's ionized completely in solution. So you have the propanoate ion from the salt, you have the propanoate ion from the acid itself. Now, according to Lee-Chatterley's principle, the fact that you have this salt, this ion coming from the salt, and of course you have it from the acid, will suppress the formation of this propanoate ion from this, because the presence of this ion, which is common to this ion, will make the amount of propanoate ion that will have come from the acid to become smaller than it should have been if this was not present. Let me explain it again and again. Now, we are looking at this. Supposing this is what we have alone in solution, you have the propanoate ion. Now, we know that this is a very weak acid. The amount of propanoate ion is going to be very, very small initially from propanoic acid alone. Now, we are now introducing this salt that contain propanoate ion again. All right, such that the presence of this propanoate ion from the salt will suppress or will reduce, if I may use that word, the amount of propanoate ion that will have been formed from the acid itself. Because according to Lee-Chatterley principle, when a system is in equilibrium and you impose a stress on such system at equilibrium, the way the equilibrium will respond is to annul the effects of that imposed stress. So if you have imposed a stress, additional stress by adding propanoate ion from sodium propanoate on the equilibrium above, the first equilibrium, and they have one ion that is common, that's propanoate ion. So the presence of this common ion will reduce the amount of propanoate ion that will have come from the acid itself. That's how a buffer system works. So a buffer system works on the principle of what we call the common ion effect. the common ion effect, because from the acid you have the ion, and from the salt that you have added you also have the salt. And so that is what we call the common ion effect. Now let's try to illustrate that by looking at this question here. It says calculate the hydrogen ion and the percent dissociation of 0.1 molar propanoic acid. Also, calculate the hydrogen ion and the percent dissociation of the same acid in the presence of 0.1 molar sodium propanoate. Now, let's quickly go through that together and see what we are going to get. Okay, so we have what are the things we have? We have 0.1 molar propanoic acid and 0.1 molar sodium propanoate. Okay, so let's see. Okay, so we have propanoic acid, CH3, CH2, COOH is an acid, a weak acid, so it gives us CH3, CH2, COO minus plus hydrogen ion. All right. And of course, according to the ICE table that I always explain to you, you have here 0.1 molar of the acid. You're going to have nothing here initially. And of course, the change that will have occurred, since this is ratio 1 to 1 to 1, all right, this will be X is used up. And of course, X will have been formed. And of course, X will also have been formed. All right, such that at equilibrium, what you have here is 0.1 minus X, and what you have here is X molar, and what you have here is also X molar. All right, such that at equilibrium, the equilibrium constant for this process is Ka is equals to X over 0.1 minus X. Now let's keep this as it is for now. Now let's now look at the sodium propanoate, CH3, CH2, COO minus Na plus. That's sodium propanoate. It will ionize completely. We're given 0.1 molar of this as well. So you're going to have CH3, CH2, COO minus plus Na plus. Now, when that ionizes completely, all of this will no longer be present, and what you're going to have is just 0.10 molar of this, and of course 0.10 molar of this. Now, if you go back to this equilibrium constant, now you find out that so we can write the equilibrium constant now in the, that's what we have here is without the propanoate ion from sodium propanoate. Now that you have propanoate ion in it, now let's see what it's going to give us. So you're going to have Ka now becoming you have X plus, because you now have two sources of propanoate ion from the acid itself, propanoate ion from the sodium propanoate. So we have X plus 1.0. Then of course you have the hydrogen ion, and of course divided by 0.1 minus X. Now this is what we have in solution. Now, without much ado, we know that the X is very, very small compared to 0.01. Okay, Now, what I mean by that, okay, maybe to enhance your understanding of this, we will assume a value for, I'm coming, let me know what the value is. I don't want to just assume, let me just look at the next slide. Okay, we have here the dissociation constant of propanoic acid, 1.32 to the power of minus 5. Okay, let me go back to my slide. 1.32 to the power of minus 5. Okay, now, so we know that Ka is 1.32 to the power of minus 5. That will be equals to, since, let me write it here, since x is far, far less than 0.1, how do I know that? This is a salt. It's ionized completely. And of course, we're going to have 0.1 here. However, this is a weak acid, as you can see from the value of its dissociation constant. So the amount of X from here will be very, very small as compared to the amount of X from here. So it's a reasonable assumption that X is far, far less than 0.1. And if that is true, and of course it is, then we can write here that this is 0.10x over 0.1. All right, so that we can say that 1.32 to the power of minus 6, because when you cross multiply, that's what you get, will be equals to 0.1x, and that x therefore will be equals to 1.32 to the power of minus 6 over 0.1. And of course, that will give me 1.32 to the power of minus 5. All right, that is the hydrogen concentration, because that is x. So now that we know x is 1.32 to the power minus s, the question says, what's the pH? Now, the pH of the solution will simply be equals to minus log to base 10 of 1.32 to the power of minus 5. I've calculated in the presence of sodium propanoate. I will calculate without sodium propanoate very soon, and then we can compare the two together. Now, let's quickly have a look at that. So in this case, please take your calculator. I'm with mine. So let's solve it together. So we have log of 1.32 exponential minus 5, and that gives me 4.88. So the pH here is 4.88. Now, what is the percent dissociation? The percent dissociation in the presence of the salt will be equals the amount dissociated, which is 1.32 to the power of minus 5, with what we started with, 0.1 molar times 100. And of course, if that is carefully done, you're going to have 1.35 times 10 raised to power minus 2%. If you what we have here, just multiply by 100, you're going to have 1.32, sorry, not 35, 32, please. It's 32, not 35, please. Let me use my eraser to clean that, please. Sorry. Okay, I can use delete. Okay, let me use delete. All right, because I couldn't find the eraser here now, but just note that what I meant to write there is 1.32 to the power of minus 2%. That is what the percent dissociation will be in the presence of the common ion. Now, let's assume the ion is not there. We come back to this equation that I start. If that, so we use this equation start here, so we can say this will imply that 1.32 times 10 raised to power minus 5 will be equals to x squared over 0.1, because we've assumed that x is very small, which is true. All right, so we can say in this case that x now will be equals to the square root of 1.32 to the power of minus 6, the square root of that. You're going to see all this thing on the next slide. Don't worry, and I will allow you time to write it. But I just want to, so that it won't be that I just reading slide, that we're solving it together. That's why I decided to do this. Okay, so let's quickly find out what our x will be with this. So we're going to have 1.32 to the power of minus 6, the square root of that, 1.32 to the power of minus 6 exponential minus 6, and that will give me 1.15 to the power of minus 3. All right, so my x is 1.15 to the power of minus 3, 1.15 to the power of minus 3, such that without the salt, the percent dissociation will be equals to x over 0.1 times 100%. And that gives me 1.15 to the power of minus 3 over 0.1 times 100. And of course, if that is done with all carefulness, you're going to get a value of 1.15. So you're going to get 1.15%. You can see the percentage dissociation here is 1.15. However, in the presence of the salt, the percent dissociation is 1.32 to the power of minus 2. So you can see the effect of the common ion, the propanoate ion that is common to both of them now. You can see that in the absence of the salt, in the absence of the common ion, the percent dissociation is 1.15, while in the presence of the salt, the percent dissociation are drastically reduced to 1.35 to the power of minus 2, which is almost like close to 100% of less than 100% of what the dissociation is in the absence of the salt. Just to explain the Lee-Chatterley's principle again and again, because you can see here now what happened is that in the absence of the salt, the amount of acetate ion or hydrogen ion, as the case may be, produced is 1.15 to the power of minus 3. However, in the presence of the salt, the amount of propanoate ion that was produced is 1.32 to the power of minus 5. Comparing the two together, you find out that in the absence of the salt, the amount is far, far greater than in the presence of the salt. That's what we call the common ion effect. That's one of the important applications of equilibrium, solution equilibrium. All right, let's look at the next slide. Let me now display the slide where you have the solution so that you can see it yourself. I want you to take your time to write. I will give you like the next 4 minutes. This is exactly what I've just explained previously. Okay, so I want you to please take your time to write that. You can see the propanoate ion concentration is 1.15 to the power of minus 3. Okay, you can see that that's exactly what I obtained in the previous slide. So I want you to please have a look at it. Okay, so what I have here on this slide is what I've explained in the blank slide that I wrote on. Okay, just for you to understand what was done. All right. I'm still waiting for those that are writing at the speed of snail to hurry up and follow through. Let me hear what your comment, any challenge. All right. Someone is asking, why did X become 0? I don't really understand that side well. It's okay. Don't worry. X did not become 0. I only said that X, okay, how did X become 0? Okay. So it's like you're having issue understanding that. Okay, that's all right. What I have just said, listen carefully, is that X is far, far less than 0.1. We have said that the acid is a weak acid. So it does not dissociate appreciably in solution. And to justify that assumption, we calculate the percent dissociation. Don't forget, I've discussed that with us in some previous classes, that once the percent dissociation is less than or equals to 5, then that assumption is a reasonable assumption. Now, why we're doing this is that we are trying to save ourselves the stress of solving a quadratic expression, because that's exactly what we normally would have solved. Okay, we are actually meant to solve a quadratic expression, but we're looking at the time it's going to take to solve the quadratic expression. Can we find a simpler route, to it. So that's why we say, okay, since the acid dissociation constant is very small, 1.32 to the power of minus 5, it means that that acid, even in the absence of anything, does not dissociate appreciably, such that we can assume that the amount of it that is dissociated is far, far less than in its initial amount. Like I used to illustrate, you have 1,000,000 naira, and after the class, you want to refresh yourself. So you bought a bottle of Coke and you bought shawarma. Shawarma, 3,000 naira. A bottle of Coke, 500 naira. So you have spent 3,500 naira or 4,000 naira. From the 1,000,000, you will still be left with 996,000 naira. It's like you have not spent anything from 1,000,000. Okay, that's the way to illustrate this concept. I hope you are getting it now. Okay, so that is exactly what I'm trying to explain here, that the amount dissociated is very small, such that we can say that we remove it from the initial amount, it will not make much of a difference. Okay, that's why X becomes negligibly small compared to the initial amount. Somebody is saying, Brain Jotter, you're always waiting for, I've noticed you're always waiting for code. You're not interested in learning, but you're only interested in attendance. And I've seen it being displayed, on different platforms. Once the class is ongoing, you'll be sharing the code so that for those who are not around can have access to it. You're not doing anybody. You are doing yourself. Okay? I will advise you to take time to listen to what you're being taught. The Lord will bless you. Okay. Somebody says, sir, how is KA 1.32 to the power minus 5? It's given. Drotolu Oluwaseyi, KA is given as 1.32 to the power minus 5. Nobody's expecting you to memorize that. That will be given. All right. Oh, somebody is saying, can you give an example that involves solving quadratic equations? Now, this is the challenge I'm going to give to you, Rodiat. What you will do, don't assume that X is small. So you don't assume that X is small. So if you do not make that assumption, then you yourself can solve it quadratically. And if you do that, compare the value you obtain to value we obtain by making the assumption. You'll find out that it's going to be very, very close to each other. Okay? So that is just the way it is. All right, thank you. I can make progress with my class now. Thank you very much. If you have any other comments, you let me know. Okay, all right, sir. What if the strong acid? Oh, if the strong acid, we'll not be talking about dissociation constant. It's simply ionization. Okay, so there is no such for strong acid. It's ionizes completely. We represent by a single arrow, so it's not an equilibrium process. What we are doing here is equilibrium processes. Thank you very much. All right, let's make progress. Okay, so that's the solution. I'm sure you have written it. Now let's continue. Okay, you can see this is exactly what I solved in the previous class. I'm in the previous slide, so you can please take your time to go through it. Okay, and again, let me just tell you, this lecture is recorded. All right, it's recorded. So all you need to do, if you do not understand it now at the moment, all you need to do is just revisit it. Go to YouTube, search for Faculty of Computing, OAU. Faculty of Computing, OAU. All right. On the Faculty of Computing YouTube page, you will see TELEPRESENCE. Click on TELEPRESENCE and you see the various courses that are on TELEPRESENCE. One of them is Chemistry 101. So click on Chemistry 101 and you have all this lecture, that you can follow through. And I'm sure by the time you go through it again, it becomes easy for you to comprehend. Thank you. I can make progress. Thank you very much. Okay. So we have here, question says compare. Okay. I've explained everything I have here. I've explained already. I've explained virtually everything that we have here. Now, towards the last towards the end of this page, you have a question there again. It says a buffered solution contains 0.10 molar acetic acid. The Ka given as 1.8 to the power of minus 5 and 0.1 molar sodium acetate. Calculate the pH of the solution and calculate the change in pH that occurs when 0.01 mole of solid sodium hydroxide is added to 1 liter of the buffer solution. Compare this pH change with the change that occurs when 0.010 mole of solid sodium hydroxide is added to 1 liter of water. Okay, very simple question. Don't be intimidated by the way it is written. Let's have a look at it together. So you have your buffer solution, you have the acetic acid, 0.1 molar, you have the sodium acetate, also 0.1 molar. You remember your Anderson-Asabach equation that we derive on Wednesday. Let's go there. Okay, so we have pH of a buffer is equals to pKa plus log to base 10, the ratio of salt concentration to that of acid concentration. And of course, this is equals to minus log to base 10 of 1.8 to the power of minus 5, but that's what the Ka is, plus log to base 10 of 0.10 over 0.10. Okay, and so this, if carefully done, will give a value of 4.74. You can please press your calculator, tell me what I should give you. You can join me to do that. .74. That's what the pH of the buffer solution is. Now the question is asking further, if you are now adding, let's go back to the page, it says you are adding 0.01 mole of solid sodium hydroxide to 1 liter of the buffer. Now what will happen? Let's look at that together. Now you have now in the buffer, you have, so these are the processes going on in the buffer. Let's write it. So you have from the acid, you have CH3 COOH to give you CH3 COO minus plus H plus. That's from the acid. Now from the salt, you have CH3 COONA. Now, because that's a strong salt, you have CH3 COO minus plus Na plus. Now, this is what you have. So, you are now adding sodium hydroxide. You are adding sodium hydroxide. Now, the sodium hydroxide will react. Of course, sodium hydroxide will react with acetic acid. Okay, so what you're going to have is you're going to have CH3 COOH plus sodium hydroxide to give you CH3 COONA plus water. All right, so you have here 0.10 molar of this. Now you have 0.01 molar of this. Okay, now since according to the stoichiometry of the reaction, the concentration of sodium hydroxide is less than that of the acetic acid. So the sodium hydroxide is a limiting reagent. So by the time it reacts, it's going to form. So what's going to happen there is that you're going to have 0.10 minus 0.010, because that's the amount. If 0.01 molar of sodium hydroxide is to react, if you have only reacted with equal amount of CH3COH, because the mole ratio is 1 to 1. So by the time 0.01 molar of this had reacted, 0.01 molar of this also will have reacted. Okay, so that what is left in solution for acetic acid with 0.1 minus 0.01. Let's take note of that. Now, here, you now have the formation because the limiting reagent determine the amount of product formed. So the amount of this form will also be 0.010 molar. Such that in the solution eventually, now let's calculate what is 0.1 minus 0.01, and that's 0.09. So for this, we can say in solution, we have acetic acid CH3COOH now. After the base have been added, becomes 0.09. And the salt, the acetate salt, sodium acetate, will be equals to, okay, you have here, you have 0.01 from the, yes, here you have 0.0, because this is 0.1, this also will be 0.1, all right? All right, so what you now have is 0.1 plus 0.01, and that will be equals to 0.11. So the acid have been reduced to 0.09, the salt have been increased to 0.11. So the pH now becomes minor, pKa, let me write it again, plus log to base 10 of the ratio of salt to acid. And this implies pH will be equals to, pKa is 4.74 plus the log to base 10 of 0.11 over 0.09. And that gives me 4.74 minus, okay, the log of 0.11 divided by 0.09. Okay, and my value is 4.65. 4.65. So what happened here? The pH has reduced from 4.74 to 4.75. What is the difference between the two of them? That's about 0.11. Okay, if you look at the difference here now, it's going to be about 0.09. Okay, 0.09, which is quite insignificant, you know. So that's to show that indeed what you have is a buffer solution. All right. So the solution again is on the slide, and this is what you have here. Okay. So you have the solution here. That what I've just written now is what I've displayed here. All right. So you have the sodium acetate ionizing completely to give us 0.1 molar of acetate ion. You have the acetic acid, okay, 0.10 minus X. All right. So what happened for the buffer is what you have here. And of course, the pH is 4.74, just as I calculated previously. And of course, you can see the percent dissociation is 1.34. Okay. That gives you less than 5%. Like Rodiat asked, don't assume that X is small. Calculate, use your quadratic expression and see what you're going to get. You're going to get something very close to that as well. Okay, so that is that. So let's see. Okay, this is exactly what I've just explained now. Okay, so you have okay, it should be plus. I wrote minus. All right. Okay, it should be plus. I'm sorry. All right. So it should be 4.83. Thank you. You can see this is 4.83, not 4.65, because I put minus. Normally it should be plus, please. All right. So that's 4.83. And of course, we are coming from 4.74 4.74, and of course we have 4.83, and the difference between the two of them is 0.09. Okay, just as I did, even with the mistake I made though, but of course the values still, the difference still remain 0.09. So you can see it does not really make much of a difference when you add a small amount of the base to a buffer solution. Okay, so you can see that now. So like I said, this note is online for you to follow through. So what happened? The next set of the question says, okay, you can see what I've just done, 0.09 pH rate. All right. So the question is that for the unbuffered solution, because the question asks you, what will happen to the pH of the solution of sodium hydroxide, 0.01 molar sodium hydroxide in water, 0.01 molar sodium hydroxide in water. 0.01 molar sodium hydroxide in water will give you hydroxide ion of 0.01. And so the hydrogen ion concentration will be equal to the ion product of water, 1 to the power minus 14, divided by the OH concentration, which will give 1.0 to the power minus 12, such that the pH becomes 12, as you can see here. So you can see the change in pH, because if this sodium hydroxide had not been added, the pH of water is 7.0. Now the change in pH is 5.00. That is, when you add the same amount of sodium hydroxide to pure water, the change in pH is plus 5.00. When you add that same amount of sodium hydroxide to a buffer solution, the change in pH is just 0.09. So you can see the importance of buffer solution. I'll go that again. The question says you're adding that same amount of sodium hydroxide to water, and the pH becomes 12.0. And you know that for neutral water without anything added to it, the pH is 7.0. So because of added sodium hydroxide, the change in pH is now 5.0. That's 12 minus 7. Take note of that. Now go back to the buffer solution. You've added the same amount of sodium hydroxide, and you find out that the change in pH is 0.09. So when you compare the two together, you will see the importance of a buffer solution. All right. So that is how to see why it's important to prepare your, especially for my students in biochemistry, chemical engineering, chemistry, human nutrition and dietetics, microbiology, animal science, plant science, soil science, and maybe my students in earth science, pharmacy. You are working with enzyme, then you need to prepare your solution in buffers, in a buffers medium, so that there won't be significant change in the pH of the solution. And like I use for illustration, the blood in your system, the blood in our system is a buffer solution that we eat all manner of junks. We take Coke, we take fruits, okay? In fruit, you have citric acid. In meat, you have proteins, amino acid, okay? So, yet, the pH of the blood remain essentially the same. You should give thanks to God for that. Anyway, that I've kept your blood system working at a constant buffer condition. All right, the next code for today's attendance, please. I'm going to write it on the slide now. Is 6U ATC. 6U ATC. Please take the attendance now as we conclude the class for this morning. Okay, we have done all this. I don't have to waste my time on this. This is and that's a batch equation which I've taught before. So it's just a repeat of what we had before. Okay, we have done all this also for a base buffer. With all this have been, it's just a repetition of what we had before. And of course, once you know the pOH for a buffer, you can, I mean, for a buffer, you can know the pH, since the relationship between pH and pOH is that pH plus pOH is equal to 14. So you can say pH is equal to 14 minus pOH. Let me use the last few minutes to listen to your comments, your challenges. Today will be the last lecture for the year. We will hopefully meet again on the 5th of January, when I'll take just 5th and 6th of January, and then we'll conclude our discussion on chemical equilibrium. I want to wish you a wonderful holiday. While you're on holiday, don't forget that tests have been slated for 10th of January. Don't forget, while you are rejoicing, and you should rejoice that you are alive to the end of the year, don't forget that you have your academic responsibility. So take time, go watch movie, go visit places, but don't forget to visit the YouTube channel to listen to your lectures again and again. All right. See, that's the way they are. Thank you very much, Malik or Dejide. Before saying it, they will have released everything. See, they are just, they are not helping themselves. I'm telling you, they are not really helping themselves. But it's okay. Yoruba will say, "Ba gúnyán nínú ewé, tá a ṣebẹ̀ nínú èpo ẹ̀pà, ẹni tó máa yó, ó máa yó. Ẹni tí ò dẹ̀ ní yó náà, ebi ló máa pákú." But kébi má lọ pa wá, please read your notes. Somebody is saying, can we get a slide for chemical equilibrium? You're not getting any slide. I said, go to YouTube. Go to Faculty of Computing, OAU. Then you go to Telepresence on YouTube. These lectures are there. All right. The lectures, Williams Deborah. I'm not sending any slide to you. Please go online. Be a responsible student. Be responsible student. Okay. And finally, I don't want to give the last code yet. I still have 5 minutes, so I can take time to listen to you. Somebody says chicken is a temptation. Hey, yeah, Yes, I've only dropped 2 code for now. I'm going to drop the next one very soon. Thank you also. Oluwapelumi, thank you. Brain Jota, hello. You have woken up. Thank you too. Hey, thank you. I appreciate the comments. And like I said, should you have any problem, how do you go about the concept of the ICE table, sir? Okay. Okay. Somebody's asking, how will you go through the ICE something? Let me see in the next few minutes if I can still do something for you. All right, let's, the fellow is asking how to go about the ICE table. Now, this is what we are saying. Let's assume we are looking at acetic acid. Acetic acid. I'm writing it again. Plus hydrogen ion. So this is our equilibrium. Now let's say we have 0.1 molar of acetic acid initially. So we put I here. Initially, we have 0.10 molar of this. Now we are not going to have anything here. We're not going to have anything here. The question is, what changes will have occurred before equilibrium? That changes will depend on the stoichiometry of the reaction. This is ratio 1 to 1 to 1. And if that is what it is, it means that if X of this is used up, why we put minus A because it's a reactant, is used up, then X of this will have been formed. We put X here as what is formed, and we put X here as what is formed, plus X plus X. So that is what will have been formed, the changes that will have occurred before equilibrium. So the equilibrium concentration is called E. So what is left at equilibrium is E, which of course will be equals to 0.10 minus X for acetic acid, and of course for acetate ion is X, and for hydrogen ion is X. So this is what we call the ICE table. All right. Initial changes, equilibrium concentration, initial concentration, change in concentration, and equilibrium concentration. That's what I mean by ICE table. I hope the fellow who has a question can now understand. All right. So all you need to do is, if you are given the Ka for the acid, like we know this offhand, we know Ka is 1 point. So Ka for this acid will be equals to the acetate ion, the hydrogen ion, and of course the undissociated acetic acid. Okay, that's what we have. If you put that according to the what we have obtained from the IC table, they become X over 0.1 minus X. Now Ka is given 1.8 to the power of minus 5. So our objective, we want to find out what X is. We are saying that X is less than 0.1, such that 0.1 minus X is approximately equals to 0.1. But like somebody said, don't let us assume. Yes, I will allow you not to assume. Please don't assume at all. You just go ahead and solve it quadratically. If you do not assume, so you have solved it quadratically, compared to when the assumption is made, you find out that your X will be essentially the same. Okay. Now, again, if you are not going to assume, let me quickly point your attention to something. Yes, we don't have to assume really. We first assume, and if I find out what X is, we don't determine the percent dissociation. If it's less than or equals to 5, then we are okay. But if it's greater than 5, then our assumption becomes invalid. Then we have to then solve quadratically. And when solving quadratically, you will get two solutions. One will be reasonable, the other will be unreasonable. It is possible you have two solutions. One is positive, one is negative. You can't get a negative concentration. So automatically you know that the negative one is not reasonable. However, you can get two positive answers. Now you have to then decide which one is reasonable and which one is unreasonable. How do we do that? So the one that is reasonable, because the value you're going to get, one will give you a value that will be less than initial concentration, and the other one will be a value that is greater than initial concentration. Can you get a value that is greater than initial concentration? Absolutely, that is not possible. So that means that the one that its value is more than that of the initial concentration is the unreasonable one. Okay, that's the way to determine that. Okay, all right. So having said that, let's quickly take down the last code as our time is over. The last code for today's class is 8K 9MY 8 Kayode 9 Mojisola Yinka, all in capital, please. All in capital. All right. I look forward to seeing you again next year. We're going to have a wonderful time together. All right. This is your last class as far as chemistry 101 is concerned for this year. Okay. Let me tell them to everybody, don't forget to bring Christmas chicken for me too. Okay, because somebody is asking for Christmas chicken. Don't forget your teacher too. Don't post the code. I didn't ask you to post code. You amazing student. Who asked you? Who asked you to post the code in comment? Leave the code. Let people who are in class copy the code. Does test cover chemical equilibrium? Yes, 10 questions from chemical equilibrium. Let me give you that as AOC now. 10 good questions. You don't have You're going to have 40 questions in the test for 40 marks. So you're going to have 10 questions from equilibrium, and I think about 12 questions from stoichiometry. And I think, if I'm not mistaken, I think 10 questions or thereabout, or 9 from atomic theory, and 7 from the first topic. Yes, the lights allow your test will cover equilibrium. You have done equilibrium before test now. Why will it not cover equilibrium? How many questions are we getting in the test? For equilibrium, 10. You are getting 40 in all. Màá tiẹ̀ mú ìtara mi sí. Mi mọ bó ṣe nǹkan bí iye tó jọ. Pé ìṣó mi. Mi ì tiẹ̀ wá rí mọ́tò láti. I'm trying to almost only back on bí mo lè ń tọ́ láti nǹkan search ni. Bẹ́ẹ̀ ṣe nǹkan ní. Okay. Okay.